Don't worry.
Okay, let's press on with our next Y chromosome talk from Amke Caliebe from Kiel. So please go ahead.
Okay, thank you for the introduction and also for giving the opportunity of presenting part of my work here, and also quite a nice slot because it's after Mikkel, and he also has done lots of this work which I'm now presenting. So it's similar to the last one. We again want to look at Y-STR haplotypes and want to estimate a population frequency, but now with a different kind of model. So we're using here coalescent theory. So that's the main difference to the first to the talk we have just heard. So yeah, this one Mikkel already talked about, but might be nevertheless I give a short recap of that. Oh, so my colors don't show here, so I hope. So I have more colors here on this than here. But okay, so it should be okay anyway. Yeah, so there are, as Mikkel pointed out, there are several methods around, and they are kind of be categorized into two types. So the first type is when we have look only whether a haplotype is different from another one or not. So we do not take into account whether so if it's similar or not, or how similar it is, but we just say it's different, and so we treat it as a different kind. So I just call them multinomial models. So what are our data? Again, we have a database here of n persons with haplotypes H1 to Hn, and also we have got the haplotype of the trace, which is identical to that of the suspect. And what we want to do now, during this talk at least, is we want to estimate the population frequency of HS, which I will call here pi. Okay, and so now for the first type of model, so we have, so one of the simplest ones, which is nevertheless used quite a lot, is the so-called augmented counting method. It's called augmented because we augment our database here with n persons by the database found at the trace. So we have then n+1 haplotypes in the database, and we simply then estimate the population frequency by looking at the frequency in this augmented database. So very simple one. And the kappa method of Brenner is then adjusting for that. So we have here not 1 over n+1, but 1 minus kappa over n+1. And kappa here is the proportion of singletons in the database. So of the haplotypes seen only once in that database. So this is also called the adjusted counting method because it's quite similar. We also have the method with Mikkel told us about, the generalized good method of Julia Serrada and also of Richard Gill. Actually, it's my favorite methods out of these because it has a good theoretical foundation, not like the kappa method. So Charles Brenner is not here. But this one has actually a very good theoretical foundation and good theoretical properties. It does not estimate haplotype frequencies, but it does estimate the likelihood ratios. Okay, so and then we have the second set of methods. So these take into account genetic information. So it does take the special shape of the haplotype into account. Yeah, so you just heard about the discrete Laplace method of Mikkel, so I don't have to say anything about it. So another method which is quite old now, so that is one of the more recent publications. So it's the surveying method. So that was the first method taking into account genetic information. So that is a kind of Bayesian method, and it uses the L1 distance of the haplotypes and estimates them our frequency pi from similar haplotypes. Okay, so what I'm going to talk about is now the coalescent method. So let's go into that. So I think lots of people are not so familiar with the Kingman's coalescent here, so I'll just give a short introduction with pictures here to show you how it works. Actually, the coalescent method is an approximation of the Wright-Fisher method, so that's very, so most simple method of population genetics. So we have here some population with a fixed population sample size, population size, and we get then the next generation simply by drawing from this population here with replacement. So this is the next generation here, and you see here this individual has this here as a parent, this one has this as a parent, and so on. And because we are drawing randomly with replacement, there can also be here individuals which have no child, and also can here individuals which have 2 or more children, of course. So that's the kind of the simplest model you could imagine. And we'll also regard the situation where we have only one parent. Okay, and so you go on until you can simulate the population evolution over time. So what we are really interested in is the genealogy of the present generation. So we do that by going back. So let's look at the first generation. We see here, we have got here 3 individuals, this one, and this one, which have no parents. So they are not relevant for the present population anymore. So we can remove them from the pedigree, and then we go to the next generation and do the same. Here we remove, for example, this one and this one, and because they are no longer relevant, we can also remove the parents if they have no other children. So we can't remove this one because this goes further down, but we can also remove this one. Okay, so we remove that one, and then we can go through each generation removing the individuals until we at last arrive at that. So then the pedigree constructed from this Wright-Fisher model. And usually it is depicted in a little bit nicer way here, as you can see here. And this guy here, so that's the most recent common ancestor of these persons here. Right, so this is then the pedigree here, or the genealogy, and this we want to approximate by Kingman's coalescent. Okay, so let me first show you some formula and some pictures again on the next slide. Okay, so the Kingman's coalescent, so that's a Markov process. I'll call it here R. It's called the N coalescent if we have a sample of n individuals. Okay, it's a Markov process, and it's now continuous in time here. And as a state space, it has the set of equivalence relations on 1 to n. So, and we start here, as you can see, that each individual is only in an equivalence class with itself. So that means, if we look here, that if we start here in the last generation, so we go then back in time, so that no individual has coalesced with other individual. Yeah? So we start, all individuals start by itself, and then as we move back in time, so some of these coalesce, and that means that the equivalence classes are combined. So and that is what is written here. So that's the generator matrix of the Markov process, and as you can see, it's very simple. So it's 1 if psi is smaller than eta, and what does it mean? So it means that eta can be obtained by combining 2 equivalent classes of psi, and only 2. So, and that means that we have got a coalescent event. So in this case, we combine the equivalent classes of this one and of this one. And if we go further back, we have here another coalescent event. So we combine the equivalent classes of these 2 with this one. Yeah, so that is the Kingman's coalescent. So as it was published by Kingman in 1982, and it's now become one of the most influential model in population genetics. Yeah, because we have a continuous time Markov process, the time until the next coalescent is exponentially distributed, and because we have here a nice generator matrix, we have here as parameter n choose 2. So this is then the first branch length, so the time to the first coalescent, and we have another random variable which is important here, and this is which individuals do coalesce. So in this case it's quite easy. So the probability that a special branch coalesces first is 2 over n, so it means that each individual has got the same chance to be involved in the coalescent event. And one can then simulate that quite easily. So I'll show you just an example. We start here with n equal to 6 individuals, and one can simulate that easily. So first we have these 6 individuals, so, and then we draw randomly which of these 6 individuals are involved in the first coalescent event. So let's suppose that are these 2 here. So, and now we have to know when does this coalescent event takes place. And we know that's exponentially distributed, so we just generate in realization of this random variable. So I have drawn it here. So this means that they are coalesced at this time here. Okay, so now we have then only 5 individuals left here at this time, and we again choose 2 of them here, and then again we generate an exponential time here where these 2 coalesce, and we proceed further choosing 2 individuals, choosing a coalescent time, and they coalesce until we have only 2 individuals left, which naturally are the ones to coalesce. So we only to generate a last coalescent time, and you see here we arrive then at this coalescent tree. And you see it's quite easily to do that, even if you don't understand about Markov processes or so, you can easily compute that with your computer. Okay, and so one of the great advantages of the coalescent method is that, as you have perhaps recognized, that you don't have to go through every generation, but you only have to go through coalescent events, which are usually much less than if you have to look at every generation. Okay, so that is kind of the backbone of the coalescent method in forensic Y-STR estimation of haplotypes, which I'm going to talk about now. Okay, so now the coalescent method, it was originally proposed in 2003 by Wilson, Wheel, and Balding, and it relies on some algorithm for simulating coalescent trees, and this is BATWING here, which was published in 1998. And so BATWING is a Bayesian approach for calculating coalescent trees. It has some priors, and then by a Bayesian approach, it simulates then coalescent trees to obtain posterior distributions by an MCMC method. So yes, and it uses also coalescent with population growth and also some other other population variations which are possible. Okay, and this is what we then used now. Okay, how do we then use the coalescent trees to estimate haplotype frequencies? Okay, so one simulates with these MCMC method n coalescent trees, and these coalescent trees have n+1 specified leaves and 1 unknown leaf. And these leaves correspond to the haplotypes. So we have n+1 specified haplotypes. These are the n haplotypes in the database plus the 1 haplotype of the trace. And the unknown leaf, so this is assumed to be drawn randomly from the population, and we want then to know what is the probability that this unknown leaf has got the same haplotype than the suspect. Okay, so I'll show you on the next slide a little bit how that is done. If you have a simulated coalescent tree, you can calculate this probability, I call it pi I, for each tree. And then you simply average out over all trees. So you have to make sure that m, the number of simulated coalescent trees from the MCMC, so from the stationary distribution, has to be sufficiently large such that enough of the state space of the stationary distribution has to be visited. So you have to simulate quite a large number usually, and also depends on the size of your database. So the larger your database, so the more simulations you have to do.
Sorry, what is the pi I?
What is pi I exactly?
Yeah, okay, perhaps it's getting more clearer if I show it to you on the next slide.
Okay.
So that is supposed to explain that. So you simulate one coalescent tree. Let's suppose it looks like that. So n in this case is 7. So we have H1, H2, H3, H4, 5, 6, and 7. And also we have here the haplotype of the trace or of the suspect. Okay, so now we have the so-called unknown leaf. So we don't know which haplotype is here. So we only know that we have some individual there, but we do not know its haplotype. So it is not specified. And so now we calculate the probability that this haplotype is the same as the trace or suspect haplotype. Okay, for this tree, so with BATWING, not only here the leaves are known, but also the internal nodes here are all known. So we know all the haplotypes of the internal nodes, and especially we know this here, this HZ. So, and you can imagine if you know HZ, so then you can calculate, if you know the mutation model, the probability that HX is equal to HS. So we just look at this branch here. The branch length we also know. So and we know hz, and then you can calculate the probability. And it will be higher if hz is some kind of near to hs, and if it's very much distant to that, so we will get then.
And so you're generating the haplotypes of the unknown coalescent points by using some mutation model.
Yeah, so the internal nodes, they are also known.
Well, they aren't in fact, are they?
No, they aren't in fact. In fact, only these are known.
Yeah.
But the internal are known by the MCMC procedure. So, yes. So what they are also of the parameters used in the MCMC approach.
If I might interrupt, they're not exactly known. That values are assigned during the MCMC iterations, and so
But
at any point in time there is an assigned value, but it's not fixed in time.
Yeah, but the random process which is assigned them must include mutation or something like that, no?
Yeah, it has a mutation model.
Yeah, that's right. That's what I was trying to get at.
But shouldn't you be interested in the place where HX and HS first come together? Their first common ancestor there. Yes. You're interested in.
Well, if I know this one,
from there, yeah.
If I know this one, then this is no longer relevant. But, well, if I know this one,
I
only
HX. So conditional.
Well, you care about whether HX and HS are the same, aren't you?
yes. If I know this one, so this is a direct ancestor of HX.
Yes.
So I know just if I put here some mutation model on it, so I can just calculate the probability that from HZ it evolves to HS. So this is then just calculated. So of course that is influenced by HS, but if I know that, it's no longer relevant. So this one, yeah.
Okay. If you know the actual haplotype there.
Yes. Yes, we know it.
Well,
We know it by the simulation of the model. So we get our so we have now a specific tree where all haplotypes are fixed, save this one. So otherwise, of course, it would be necessary to look at this one. Yes, and so that's how we then calculate the pi I, and then we get the average over that. And you see also why M has to be so large, such that we have a good representation here also of the internal nodes. Okay, so here are some simulations we have done just to check how this coalescent method works. So we have here 7 loci, and we have a simple stepwise mutation model here with this mutation rate, 0.003. And yes, we have sampled a kind of reference population, which is to represent the whole population of 50 million haplotypes. So of these 50 million haplotypes, we have 50 million haplotypes, and of the different types of the haplotypes, we then know the frequencies, and we assume these to be then the truth, which we want to estimate. So, and we sampled from that 5 databases of size 100 and 200 each, and from each of these databases, we estimate the probability pi from the databases for only the singletons, because we are mainly here interested in the singletons, so the haplotypes which are only ones in the database. So these are the rare ones, so they are difficult to estimate, and also some of these methods especially apply kind of only to singletons or very rare haplotypes. Okay, so and here we compare then 4 methods. So first the augmented count estimate, so this very simple count estimator, so the kappa method, the surveying method, and the coalescent method. So when we did this simulations, so that was 2013, so we didn't know about the generalized good method, so we hadn't included that, so we will do that later. And also the discrete method was only developed after that. Okay, so here are the number of singletons we have in the databases. Remember, we have got 7 loci, so yeah, we have here 5 databases of size 100, and you can see here we have as number of singletons about, well, 80 to 90% singletons. In a database of size 200, we have, of course, less singletons, so here they are, well, from, let's say, 65 to 75% about. Okay, and for each of these singletons, we take it out of the database and try to estimate it from the rest of the database by the different methods. Okay, here is, if we look at the databases of size 100. Here on the x-axis we have the true match probability, and here on the y-axis we have the values given by the estimators, by the different estimators. Okay, so you see here the red dot, so that's the coalescent method, and the blue cross, so that's the surveying method. Oh, so I'm lucky that these colors are here now. Yeah, you see for the augmented count estimate, so that's a very simple one. So we have then simply to calculate 1 over 100 in this case. So this only gives us here this line. So it doesn't depend what the haplotype looks like, but simply this number 1 over 100. So we get here this line here. And for the kappa estimate, so that depends a little bit on how the database looks like. So we have 5 databases, so we have 5 kappa estimates then, and they are here between these dashed lines here. And this one here is the median of that. Okay, and here we have the diagonal, which is, yeah, of course, the one we are aiming at. And one can see here, for example, that the augmented count estimate, so yeah, it's really biased, which is also not surprising because we always observe the haplotype once because it's conditioned on that. We also always include it into the database. But we can see also that the surveying method, so that more or less a rather old method, so it's also quite biased, as you can see here. Okay, so and then we have then here the coalescent method, which shows kind of correlation with a true value, so that's quite good. And also the kappa method is not so very bad here if you look at that. Okay, here is the bias calculated then for the methods. Yeah, you can see here, as we have seen in the picture, that the surveying method has a rather large bias, whereas Brenner's and the coalescent method, if you look at these here, they are, well, about the same size. One could also look at the mean squared error. One has then similar results here, that we have a large mean squared error for the surveying estimator and smaller ones than for coalescent and Brenner's method. Yeah, and also one could calculate correlation between the estimated value and the true value. Yes, and you can see here the values we have got. So they are not so bad for the surveying estimates. So perhaps if one looks again at the picture here, perhaps this can be calibrated such that might give better results. Okay. Yeah. So let us looks differently. So let us summarize now here what we got out from our simulations. We see that with respect to bias, we see here that we have more or less better results for kappa and coalescent method, and the same applies to the mean squared error. Correlation, we can see some correlation, although not perhaps as high as we would like for surveying and coalescent estimator. So now we come to something which you cannot see because I haven't shown it to you, and that's the computational intensity. And for the augmented kappa method and for the augmented counting method and the kappa method, you can calculate it, of course, immediately. So they are really good for computational purposes. For the surveying method, well, it needs kind of a bit more calculation, but quite doable. But the coalescent method is really computational intensive. So that's really one of the drawbacks of the coalescent method. Okay, so now it's something which we want to do now, which we are working at the moment. So the coalescent method, so one of the advantages is that it can capture the genealogy, as you have seen. So it's based on that. So we can capture genealogy, of course, only as far as it is represented in the database. But at the moment, a population substructure is not included. So we want to include that because that's one of the major issues here. Yeah, we like to include a theta correction, but yeah, as Nico pointed out, we're not quite sure which theta to use that, but well, it's work in progress. I think we have to arrive at some conclusion how to handle that. And we also want to look here at the structured coalescence. So the structured coalescence can handle substructures. Yeah, therefore it's called that way. So we can also include that. Okay, but before we can do any more refinements, The problem is that it's really rather slow. So we can't do a lot of simulations, include many methods, before it's faster. So that is the imminent task here. So we have to improve the speed of the coalescent method. And that is what we are working on right now. So what we want is we want to implement it on FPGAs. So probably most people are not familiar with that, so I wasn't either some a year ago or so. So FPGAs are field programmable gate arrays, and they are kind of programmable hardware. So they have a kind of hardware which you can program in such a type such that it is optimal for a specific computational task. And then it is usually much faster than the methods used, the computer you're using now. So usually they get a speed up of, well, larger than 100 compared to a single quad-core PC, and usually you often have a speed of larger than 1,000 or even more. So they're quite powerful, and if you use more of them, you just can multiply it by that. And they are capable of massive parallelization. Okay, so how do we do the parallelization for the coalescent method? So, well, the simplest way to do that is not to simulate one MCMC chain, but to simulate multiple of them in parallel. So we could have then independent simulations. So the drawback is that there's some memory required. So we have got a Markov chain, so we only have to keep track of the present state. But, well, that is also a little bit a problem for the FPGAs. So they are not good at storing a lot of memory. The other thing we want to try out is we're looking at the MCMC algorithm. And in the MCMC algorithm, so let's think perhaps of a Metropolis-Hastings algorithm. So a new coalescent tree is proposed, but it's not always accepted. So most of them are rejected, so we have an acceptance probability of, let's say, 20% about. And so it would be a possibility just then in the acceptance rejection step of the MCMC to simulate more of these proposed trees and then take the first one which satisfies the condition. So we have here a dependent outcome, so we have to synchronize it after one of the trees is rejected. But here on the upside we have here little memory required. So we want to incorporate these two methods here. Now we have thought about which basic model to take for that. So there are more or less 3 methods around for simulating coalescent trees for Y-STRs. We have BATWING, where originally the coalescent method is already implemented, BEAST and migrate, which we looked at. So BATWING, so that's programmed in C. So at the moment there is no parallel mode available. So BEAST is programmed in Java. So we have here a possibility of a parallel mode. And also it says that it can be utilized on GPUs, which are similar to FPGAs, so that might also be useful. And migrate is in C. We have also here parallel mode available, and we also have here message passing systems available such that it can be used on computer clusters. Okay, so if you look at this in the first instance, you would say, well, perhaps BATWING is not such a good choice. Let's see about that. So, but with migrate, we have seen that this is not this is only at the moment applicable for deployed data, so not for Y-STRs. So we had to remove migrate from our program here. So what we are mainly interested in is now then in comparing BATWING and BEAST, and we have done some. I've got a new PhD student from computer science, and he has done all the stuff here. So he has done some simulations, and this is the result when we compare BEAST and BATWING here. The blue ones here are BEAST. BEAST here in the sequential mode. The red ones are BEAST in the parallel mode, and the black one here is BATWING. And we see here on the y-axis the runtime in seconds, and we have here a database size. So we took the databases I've just shown you. There's 5 databases of size 100 and the 5 databases of size 200, and these are then the average runtimes. Okay, you can see here, if you have the lighter color here, you see that is if the library Beagle is used and the implication for the GPU. And you can see here that for what we have simulated here for the STRs, so it seems that the GPU isn't really used, and if you look in the program, yeah, it seems it's turned off for these, so it cannot be used here for the STRs. So that's not really improvement here. You can see here, if you compare here the sequential to the parallel mode, yeah, it is faster. But what you can also see, that BATWING is even faster, although it is only here in the sequential mode. So you could improve this quite a lot if you parallelize that. Not a good word for a presentation. Yeah, so what we are doing now is we want to use BATWING as a template for the implementation of the MCMC for FPGAs. We also, so then we want to parallelize it. So it should be faster after that, so much faster. And we want to integrate some concepts of beast and migrate where this might be useful. So, and we hope that after all these proceedings, we will be able to make it a lot faster. So that's it. I just want to thank all my collaborators. So Mikkel, he did all of the simulations I showed you for the comparing the coalescent method to the other methods. So then it's joint work with Michael Kraftschak from Kiel and Sven Gundlach. He's the PhD student from computer science, and also this is one of my former PhD student, Arne Jochens, and it's also in collaboration with Sascha Willweit. He is at the Charité University in Berlin, and he also looks after the Y-STR database. So thank you for your attention.
Yes, very nice talk, especially finding that my 20-year-old method does.
Yeah, fortunately I share.
Ian Wilson did all the coding, so nothing to do with me. But he'll be pleased to know it's faster. So, any questions?
Just a question about the FPGA's implementation. So I didn't, because I'm colourblind, I couldn't appreciate any of the differences at the end there.
Sorry.
So basically, there are no real speed up differences in the parallel version. Basically, is what you're saying. Is that right? Because I can't see.
Yeah.
Okay. So we have here this column and this column. So
sorry?
If we compare this column, so the blue one is without GPU, and the lighter blue one, the left one is without GPU, and the right one is with GPU. And you see here no difference. And
So it comes to my question. So is it the case you simply took the original source code, which may have been written in C or Java for those algorithms, and you didn't adapt it anyway, you simply...
So we haven't implemented it yet, so we just now checked out which program to take. So we are going to use BATWING as a template, but of course we will have to program it separately, because we have to use a special language for that.
Right, then I don't exactly understand what these results are.
But you have to kind of template. So, for example, if if the beast here already works well with GPUs, so an alternative might be to use that and to make it kind of faster with the GPUs, for example. Yeah, so you have also if you want to implement it, so in the parallel version or so, you could use it as a template, but that's not really useful then. But we perhaps will use some of the ideas. But yeah, you have to kind of first have to something on which to draw your new problem. Yeah.
Any other questions? If not, thanks again to both the speakers. I want to